based on its physical state. So we're going to, in this subsection in chapter 3, we're going to identify the different physical states as well as some of the properties of those different states of matter. So in our class, we're going to be looking at 3 physical states. Or sometimes you'll just see the word state, or sometimes just phase. We're going to have the solid phase or the solid state. We're going to have the liquid. And then we're going to have the gas. All right, and we encounter these 3 physical states or phases on a regular basis. Actually, there's one substance that you're intimately familiar with that exists in all 3 physical states: solid, liquid, and gas. And you see it all the time, right? And that's water. Water exists as a liquid, it exists as a gas, it exists as a solid. For instance, solid ice is in your freezer, liquid water is what you drink, and then when you boil water, you get water in the gas phase, right? So water is something that exists in all 3 states, and if you're ever confused about the transition and going between one state and another state, just go back and think about water, right? The one thing that you're most familiar with. So these 3 physical states are going to have little shortcuts that we use to reference them. So solids are often abbreviated S, small s, surrounded by a couple parentheses. Liquids are often abbreviated small l, that's an L, by the way, if it's hard to tell. And then what do you think gas would be? Small g. Right, so solid, small s, liquid, small l, and then gas would be small g. So what's the difference between these 3 physical states? We're going to start with the solid, first of all. So in a solid, the particles are going to be packed very close together in an orderly fashion. So the solid particles, they're so close together they can't get any closer to each other. There's an arrangement to the solid particles. There's an order to them. And the other characteristic is that the particles are not free to move around. In other words, they're locked in place. So they cannot move, but they may be able to vibrate a little bit. So if I had a sample of a solid, for instance, right, this would be a good depiction of those solid particles in that sample, right? So each circle here represents a solid particle. They're packed really, really, really close together, and they can't really move around, right? They're locked in place. They can maybe vibrate a little bit, but they definitely can't start moving past each other. As a result of the arrangement of the solid particles, right, what we're going to see is that solids are going to have a fixed or definite shape, and a fixed or definite volume. Right, and what that means is that the shape and the volume do not change. All right, so for instance, if I have something that's a solid, so let's say this stapler, for instance, right, it has a particular shape associated with it. It's stapler shaped, for lack of a better descriptive term, and that shape doesn't change. The particles of this thing are packed really close together, and you can't really change the shapes by squeezing it or by trying to compress it. The volume that it occupies is also constant, it's not changing, right? The amount of space that this occupies is unchanging as well. And that has to do with the fact that the particles here, they're locked in place, they're not free to move around. Right? So solid particles are packed really close together. They're not free to move past each other or to move around at all. Liquids, on the other hand, have characteristics that are going to be different than those of the solid state. So in a liquid state, the particles are close together, but not as close as in a solid, right? So that's the first difference. They're not packed as closely as in a solid. The second difference is the freedom of motion of the particles. So here in a liquid, the particles can slide past each other. Relatively easily. Right, and we saw that was not the case in a solid. In a solid, the particles were locked in place. They weren't able to move with any degree of freedom. As a result of these two characteristics of the particles themselves, liquids are going to have a definite or fixed volume. All right, so the volume that the liquid occupies is not going to change, but the shape is not definite. So it's indefinite shape. It actually depends on the container that the liquid is in. All right, so let's say we had this bottle of, I assume it's water. So what's the shape of the water? What shape does it adopt? Yeah, it takes the shape of the container, the bottle, to the extent that it fills the bottle, right? So we can say it's cylindrical or it's bottle shaped. And then what would be the volume of the water? Well, we could measure it, right? We can use some sort of a measuring device like a graduated cylinder. We can just look on the label here and it says it's 591 milliliters. I think it's a little bit less than that. So if I take this water from the bottle and I pour it into a different container, let's say I pour it into a sink, and I plug the sink before I pour it in, and I pour it into the sink, what would be the volume of the water? It would be the same, right? Assuming that the sink is plugged and the water can't drain out. What would be the shape of the water at that point? It'll be the same shape as the sink, right? So it'll be more, flat to the extent that it actually fills the sink. So that's very different than a solid, right? If you take a solid, like my stapler, right, it has a particular shape. If I put it into the sink, it still has the same shape. It's not going to change. And the amount of space that it occupies is not going to change as well. All right, so there are some differences between solids and liquids in terms of the particles, which leads to differences in terms of the shape. So the third physical state here now we're going to take a look at are the gases. And the gases are kind of like on the extreme end, on the other extreme compared to solids. All right, so in a gas, the particles are very far apart from each other. Right, so that's a big difference between the other two states. The other big difference is in terms of the motion of those particles. So here the particles are in constant, random, rapid motion. So what that means is that the particles of a gas are always moving around. They're zipping around with a great deal of speed. So in this room right now, you're surrounded by a bunch of gases, right, that make up the air that you're breathing in. And those gases are the particles themselves are very far apart from each other, relatively speaking, and they're zipping around. They're moving around like this. They're always moving. They're never constant, or they're never stationary. And when they move around, they're eventually going to run into each other. When they run into each other, they just bounce off of each other. And then they eventually bounce into the wall. So right now, right, what's actually happening on a really, really small scale is that there's a bunch of the carbon dioxide that you're breathing out and the oxygen that's in the room and the nitrogen are hitting the walls like this all the time. Every single second you have a bunch of these collisions happening really, really fast. But they're tiny things that are hitting the walls. They're hitting the ceiling, they're hitting the floor. Guess what else they're going to hit? Yeah, they're hitting you also. Right? You're being bombarded right now with a bunch of gas particles. And that just has to do with the nature of gases, right? The particles are spread out and they're in constant, random, rapid motion. They're going to run into things. We'll talk a lot about gases when we actually get to the gases chapter down the road to explore this behavior a little bit more. So what this means in terms of the shape and the volume now of our gases is that it's going to depend on the container that these gases are in. All right, so we can say the shape of a gas is indefinite, right? And what that means is that it depends on the container. And then the volume of a gas is also indefinite. This would also depend on in this case, the volume. Of the container, right? And just to clarify that, we can say that the volume of a gas is simply the volume of the container that it is in. So we can say a gas expands, or a gas fills the entire volume of the container it is in. Right, so to give you a sort of a visualization of this, if I had a container like that and I had a few gas particles in there, all right, they're spread out and they're constantly moving around. right? They're zipping around that container with a great deal of speed, and they're going to run into each other. They're going to run into the walls of the container all the time. Right, so there's some big differences between the solid state, the liquid state, and the gas state. Right, and those are summarized here on your table from your textbook. So we talked about the shape differences, the volume differences, the arrangement of the particles differences. We didn't talk a whole lot about the interaction between the particles themselves, but we can make some pretty safe conclusions, can draw some conclusions based on the arrangement of the particles themselves. So in a solid, the interaction between the particles are very strong, right? There's a strong attraction between them that keep them close to each other. And that's very different than in a gas where there's essentially no force of attraction between the particles, which means they can spread out a lot more. And then you have sort of moderate interaction between the particles in the liquid phase, right? And we talked about some examples already of your solid, liquid, and gases. All right, question so far on solids versus liquids versus gases. So that's a classification of matter based on the physical state, right? The actual phase that something happens to be in. Now we're going to take a look at some of the properties of matter itself. And we have two general types of properties that we're going to see. We're going to be looking at physical, and then we're going to be taking a look at chemical properties. So properties, by the way, the word properties is just another name for characteristics. Right, you'll see this a lot in chemistry. There's special terms that we use that mean regular things. Properties is one of those terms. So a physical property or a physical characteristic is a property, or are properties, I guess, looking at plural, are properties that can be observed without attempting to change the substance, whatever that substance is, into something else. Right? So when you report on the physical property of something, all you're doing is describing its characteristics. So for instance, we can say, that if I borrow your water again, we can say the water is a liquid, right? Just by making that observation or that observation, I'm not trying to change the water into something else. Right? We can measure its volume. We can stick it in a graduated cylinder and record its volume. That would be an example of another physical property. We're not trying to change it into something else. We can say the water is colorless, right? By saying that it doesn't have a color associated with it, right? We're not trying to change it into something else as well. Right? So there are many, many examples of physical properties. The color, as we mentioned, or lack thereof. The density of something. You can measure the density without trying to change it into something else. Right? Measure its mass, measure its volume, and divide those. We can record the boiling point or the freezing point of water without changing the water into something else, right? It still is going to be H2O. And that's the key idea behind physical properties, characteristics that can be observed or measured without changing the substance into something different. For copper, for instance, right, we can talk about the color of it, the fact that it's shiny, conduct heat or electricity, its physical state, when it boils or boiling point and its melting point. We can make all of these observations about its characteristics without changing it into something else. So, knowing what a physical property is then can lead us into identifying and judging or determining some of the changes that a substance can undergo. And one of the main changes we're going to take a look at here are physical changes, right? So we're going to take a look at physical versus chemical properties, but also physical versus chemical changes. So what a physical change is would typically involve a change in the physical state or shape of something. The key thing when a substance undergoes a physical change is that its identity does not change. So we have the same substance. So for example, a physical change would be something like if you have ice, which is just water, frozen water, right? So we can say solid water. So if you have a block of ice sitting out on the table in front of you, like right now, what happens to the ice? Yeah, it melts. So what does it turn into? It turns into liquid water, right? But it's still water in both cases. It still is, if you remember, H2O. We have not changed the chemical makeup or the identity of the substance. And physical or changes between the physical states are really good examples of physical changes, right? Similarly, if we take that liquid water and we boil it, it still is water, but now it's in the gas state. So the identity remains the same. Just the physical state changes. Sometimes we can have physical changes that involve changes in the shape of things, right? So for instance, if I have a gold nugget and I take a hammer and I pound that gold nugget over and over and over and over and over again, and I turn it into a gold sheet, have I changed the identity of that substance? It still is gold, right? The only thing that's changed is what it looks like. It went from a nugget form to a more flat, sort of spread out form. It still is gold. If I have a piece of paper, make sure I choose a sheet here. All right, so I got my sheet of paper. Now let's say I do this to it. Have I changed the identity of the paper? Is it still paper? Yeah, it's still. What I've changed though is the shape of it, right? It went from a nice rectangular shape to little pieces, but it still is the makeup of the paper is still the same. A bunch of cellulose and other things in here. Right, so changes in shape, changes in physical state, those are really good examples of physical changes. The identity remains constant as the substance undergoes a particular change. So physical properties, characteristics you can observe or measure without trying to change a substance into something else, like color, density, shape, etc. And physical changes that are changes that something undergoes without it changing into something brand new. Those are very different than chemical properties and chemical changes. So what a chemical property or a chemical characteristic is a characteristic that can only be measured or observed trying to change a substance into something else. So for example, we can say that gasoline is flammable, right? That's a characteristic or a property of gasoline. And what does flammable mean? You can burn it, light it on fire, and when you burn gasoline, what does it turn into? Is it still gasoline at the end? That would be great, right? If you burn gasoline and you end up with gasoline, you don't have to go to the gas station anymore. It doesn't work that way. So you burn gasoline, you end up with a bunch of different things. A bunch of gases that come up, carbon dioxide and other things. And you can only measure that or observe that characteristic of gasoline by changing it into something else. Right? And that's different than a physical property where we can observe the characteristic of gasoline or a substance by not changing it into something else. So for instance, saying that gasoline is a liquid would be an example of a physical property. Right? You can make that observation without changing it into something else. You can only determine that gasoline is flammable by trying to change it into something else, by actually burning it, or trying to burn it. And then we have our chemical changes now that are very, very different than physical changes. So what a chemical change is a change in the identity of a substance. So when something undergoes a chemical change, a new substance or substances is or are formed that have different chemical and physical properties than the original substance. Okay. Can you think of an example of a chemical change? Chemical change? Yeah. Digesting food? Okay. So walk me through that thought process in your mind. What are you thinking? So imagine the food that you ate was whatever, a piece of toast. Okay, so at the tail end, yes, you're exactly right. So obviously what you end up with is not what you started with, but it has very different properties. But why do you eat stuff? Why do you eat food? For energy. Yeah. Right? So when you eat that piece of bread, right, which itself has chemical and physical properties associated with it, it undergoes a bunch of chemical changes in your body that converts it into other things, like energy and like you're breathing out carbon dioxide and water vapor. Right, as a result of that process, and carbon dioxide and water vapor are very different than the bread that you ate. So very different physical and chemical properties of substances that you end up with compared to the bread that you started with. Right? And that's the hallmark of chemical changes. So what you just mentioned, digestion, that's a biological process, but that can't happen without chemistry, right? It involves a bunch of chemical changes. It's the same idea with the gasoline, right? The gasoline is the food that your car eats, to put it in a non-technical term. But it's the same idea that happens. And the same thing that happens. The gasoline gets turned into other things, like carbon dioxide and water vapor. And why do you put gasoline in the car? To give the car energy, right? To get from point A to point B. You eat food to get energy, to get from point A to point B and to do other things. So it's the same idea. They both involve chemical changes, right? And as a result of those changes, guess what? Energy gets released that we can use for a variety of things. All right, so we've seen several important differences between physical and chemical properties and also physical and chemical changes, right? Another good example of a chemical change would be the rusting of iron, right? So you start off with iron, it rusts, it turns into rust, which is very different than the iron that you started with, right? If you drive a rust bucket like I do, you know, it didn't start off being a rust bucket, it was brand new iron in the car, and then over the course of time, it turns into rust, which has very different properties than the iron. The rust falls off, you end up driving less and less of a car as time